Now by this time you are familiar with the all types of stresses, that is the stress due to the tensile force, compressive force, shear force, transverse shear, torque, bending moment. Now once these stresses are known to you, you have to develop the state of a stress for a given element and you have to identify the principal stresses. The principal stresses are those stresses at which the normal stresses are maximum or the shear stress will be maximum or minimum at particular angle. Those are called as the principal stress angle and the plane of maximum shear. And then once we know the maximum value of the normal stress and shear stress, then we'll discuss the different static theories of failure. The theory of failure we have divided into two parts. First we'll discuss the static theory of failure, that is the static load. It means that the load is gradually increased from 0 to certain value and the magnitude and the direction of the load is remain constant. The other theory, which is called as the fatigue theory or the dynamic theory, in which the load will vary continuously in magnitude and direction. So that is a different issue and we'll discuss it later on. So all the machine members are subjected to different types of loads that may be acting because of energy, torque, power transmission, or because of their self-weight, frictional resistance, inertia, centrifugal forces, or due to temperature gradient. That is thermal stresses we have discussed in the mechanics of material. So this type of load may be classified as a static and dynamic, that is a variable with respect to time, maybe in direction or in both direction and the magnitude both. Machine part will fail when the stresses induced by the external forces exceed their strength. The external loads cause an internal stresses in the element. We are interested here what are the internal stresses are developed in the given element, and the component size is depend on the stresses developed. In the analysis of the failure, we have to first identify whether we have a static load or we have a dynamic load. Now the first one is a static load. The load does not change in magnitude and direction and normally increases gradually to a steady load. So if I want to show the static load on the load versus time diagram, initially the load is 0 and then it is gradually increases. So this time the load will increase gradually from 0. So gradually it is increasing. After some time, the magnitude of this load is remain constant. This type of load is called as the static load. So if the member is stationary, then the load will be always a static load. So there are number of situations we have to investigate the static load. But in the number of situations like internal combustion engine, the load is continuously vary in direction as well as in magnitude. So in that case, we have to find out the dynamic load. This type of load changes in magnitude or direction or both with respect to the time. So suppose we have the load diagram. On y-axis we are going to plot the load, x-axis is time. In that case we have the variation in the load. So the variation of a load can be shown like this. This load is changes its magnitude and direction continuously. One time it is positive, second time it is negative. So the load direction as well as the magnitude of the load will continuously vary. In the second case here, the load is variable but changes from positive to lower value of positive to higher value of positive. So this time the direction is not changed. This time here the direction will change as well as the magnitude also change. This one is a very common example in the case of connecting rod of an internal combustion engine. In the impact load and the load applied with a certain velocity and the shock load suddenly applied to the load are also the some type of dynamic load that you have to consider while designing the theory of failures. In fact, here the determination of appropriate load acting on a machine member is a critical and is always a challenging task. All the stresses and deflection analysis is useless and the component cannot function satisfactorily if the operating loads are not calculated or predicted correctly. Sometimes the operating loads are easily determined. Example, the load on a shaft running at a known speed and transmitting a known value of the torque. But often the loads are difficult to determine. Example, the load on the vehicle chassis, which depends on the road condition and the driving practices. This type of load where we are driving a vehicle on the road condition will continuously change. Even every driver has a different way to drive the vehicle, so load conditions are really difficult in such situations. So sometimes it is very easy and sometimes it's a very really challenging job to calculate the load. That is the state of stress is very difficult to find out. Let us first understand what exactly the failure means. That is the failure criteria. So when a machine element is said to have a fail when it ceases to perform its intended function. Now this function we should have to define first, and if we fail in that, it will be called as the failure criteria. Just like you're familiar with the Taylor's tool life. So there are a number of ways to define the Taylor's tool life. That is the Taylor's tool life we can express in minute. Taylor's tool life we can express on the quantity of the chip collected or the number of component produced. So similar to this, we have to define here first the failure criteria. It may happen if the stress or deflection crosses the acceptable limit. Suppose we are investigating the ductile material, then we are familiar with the stress strain curve for a ductile material. Initially, the curve is straight, that is the stress is proportional to the strain. That portion we can represent by a straight line, and for this one we have slope is same as equal to Young modulus, which is defined as a stress divided by strain. After this, yielding will occur and we have the stress strain diagram will go like this. There is a local strain hardening will form, and then again the stress will increase. It will attain the ultimate value at this point. After that, again you start stressing it, the material will fail at a certain value that will be called as the fracture limit. The maximum strength in the case of ductile material corresponds to SUT. Yielding will start at a value equal to SYT, and we have a fracture strength is equal to SF. So up to SYT, the material will behave elastically. So that is a region where we can use the ductile material. So that is why it is said that the excessive deformation of a particular element may lead to unwanted interference between the machine element. So if you straight it beyond, there is a permanent set, and if we are using the piston and cylinder arrangement, then the material will expand, and it may be possible here that the interference is between the cylinder and the piston that will jam the machine, that is the cylinder and the piston in this case, and therefore the deformation is considered as a failure criteria. Whereas in the case of brittle material, hardening is not possible. So we'll get an approximate curve in the case of brittle material. This figure can be shown like this. So yielding is not possible, and you will get approximate graph of the brittle material is shown in this figure. So this ultimate value in this case will be called as ultimate stress in case of tension, and the corresponding value here will be called as the ultimate strength during the compression. What we observed in the case of brittle material, the value of SUC is always greater than SUT. Whereas in the case of ductile material, the value of ultimate strength in compression is same as the ultimate strength in tension. So we have to define the theory in two different ways. One is for ductile material and second is a brittle material. Theories of failure for ductile material for static load will be based on the yield criteria, whereas the theories of failure for brittle material is based on the fracture criteria. In case of brittle material, we'll study the maximum normal stress theory, brittle Coulomb-Moore theory, and the modified Morse theory. And for ductile material, we'll study the maximum shearing stress theory, distortion energy theory, and ductile Coulomb-Morse theory. The examples of ductile material we can take as a steel, aluminium, and examples of brittle material you can take as a glass, cast iron. So when the stress is developed in a ductile material reaches the yield strength and it start yielding, and excessive plastic deformation will occur. Therefore, the yield strength is taken as a failure criteria for ductile material. Whereas in the case of brittle material, very small plastic deformation will occur. So in brittle material, very small plastic deformation occurs and the fraction takes place. Once the stress developed reaches the ultimate value of the tensile strength or ultimate value of the compressive strength. So in the case of brittle material, the ultimate tensile strength or ultimate compressive stress is considered the failure criteria for brittle materials. So both these ductile and brittle material, the failure criteria is different. In the case of ductile material, we have yield criteria, so we'll select the SYT. In the case of brittle material, criteria is ultimate value of the strength, either in tension or either in compression. There are the other failure criteria also, particularly in the case of bearing pressure and the wear. So bearing pressure normally come in the components rubbing against each other with applicable relative velocity. Say for example, we have bearing, clutches, brakes. Whereas the wear will also take place if the components having a sliding or rolling motion. Examples will be the gear, bearing, bushes, piston, cylinders. In all theory of failure, we are interested in a factor of safety and the allowable stresses. The factor of safety is a measure of reserve strength provided to take care of any unexpected or unpredicted conditions that may arise due to uncertainties in the properties of the material, magnitude and the direction of the load or the operating conditions. In that case, we will define the factor of safety. So by definition, we have factor of safety, which is represented by lowercase n. Factor of safety n we can define as the strength divided by allowable stress. So suppose we are using here the strength equal to SYT divided by the sigma allowable. This definition we will going to use in the case of ductile material. In the case of brittle material, this value was given as n equal to the ultimate value of tension divided by the sigma value that is allowable. It can be SUC or SUT, depends what is the maximum value of a normal stress. So this definition we will going to use in case of brittle material. Sometimes the factor of safety is also defined on the basis of yield shear stress, that is SYS divided by allowable shear stress, which is again used for ductile material. The SUC value was taken as a negative value and SUT value was taken as positive. If your allowable stress is positive, then you can use SUT. Otherwise, if the allowable stress, that is the maximum principal stress, is negative, then you can go for SUC. Thus we observe is that the value of factor of safety depends upon the effect of failure, that is the level of severity, cost, danger involved. So we have a different value of the factor of safety if we go for the agriculture equipment. If we go for the factor of safety while designing the aeroplanes component, or the factor of safety that we are using in the spacecraft, where danger involved is a very high value. In that case, we can go for higher value of factor of safety. Secondly, the factor of safety also depends upon the type of load, that is a static load or the dynamic load. Accuracy in the load calculation, it is also based on whether we are using a ductile material or brittle material. In addition to this, you have to consider the reliability, service condition, that is a normal or corrosive, or the temperature level, or the manufacturing quality, that is a variation in the desired dimensions and the quality, as well as the cost involved also. So in general, the factor of safety is defined as the strength of material divided by the allowable stresses or the design stresses. So numerator here in all these definitions represent the strength, and denominator is represent here allowable, or we can call it as design. So number of times the author will use term as a design stress, or he can call it as allowable stress also. So in the case of a ductile material, the yield strength was taken as a criteria. For brittle material, the ultimate strength are taken as the critical stresses. And there is no sharp line demarcation between the ductile and brittle material. But we can say here that is a rough guideline I am giving you, that the percentage of elongation is less than 5%, you can treat as a brittle material. So if the elongation percentage will be less than 5%, so this is a rough estimate, then you can treat the material as a brittle material. And in the case of ductile material, the elongation can also exceed greater than 15%. So basis on elongation also, we can classify the material as a ductile material or we can classify it as a brittle material. In the next video, we'll slightly review all type of stresses, that is the normal stress, shear stress, normal stress due to the axial loading, normal stress due to the bending, shear stress due to direct shear, torsional shear stress, and the complementary shear stress due to bending. Once we finish the basic type of stresses, then we'll revisit state of stress and we'll introduce you the Mohr circle, how to calculate the value of the shear stress using the Mohr circle for different state of stress. The video you are watching is from the app, which is the Mohr class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.